Welcome back to the Deep Dive. Today, we're going to put on our noise-canceling headphones, but we're going to do it to ask a really weird question.
Which is, how do you engineer silence?
Exactly. Our mission today, looking at our source material on active noise cancellation, is to figure out how we make things quiet by, well, adding more sound.
It sounds like a total paradox, doesn't it? But it really starts with the fundamental truth that we tend to forget.
What that?
We live at the bottom of an ocean of air, and sound isn't, it's not a thing you can just block like a wall. Sound is an event.
That's such a great way to put it. So the roar of a jet engine that you hear, you're not hearing the engine itself. You're feeling the air molecules around you getting violently compressed and then stretched apart. It's a pressure wave.
Right. And we model that wave with the simple sine wave everyone remembers from school. And most people know two things about it. Amplitude.
That's the volume, how high the wave is.
And frequency.
The pitch, how fast the waves are coming.
Exactly. But there's a third property. And for active noise cancellation, this one is everything. It's phase.
Okay, phase. Let's break that down because this is where the magic starts.
Think of the wave cycle like a clock face. Simple as that. The very top of the wave, the peak, that's 12 o'clock, or 0 degrees.
And the bottom of the wave, the trough.
That's 6 o'clock, 180 degrees. Phase just tells us where the wave is in its cycle at any exact moment.
And knowing that position is what lets us cancel it out.
It is, because it lets us use the fundamental law of all wave physics, the principle of superposition.
Superposition. That sounds heavy. Very textbook. What does it actually mean in simple terms?
It's surprisingly simple, really. It just means when two waves meet in the same space, you just add them together.
It's just like simple math.
Yeah, that's it. So if two waves are in phase, their peaks hit at the exact same time, they help each other. 1 + 1 = 2. The sound gets louder.
Like two people jumping into a swimming pool at the same time to make one giant splash?
Perfect analogy. That's called constructive interference. But for our headphones, we want the exact opposite.
Want a perfectly flat pool, we want destructive interference.
Correct. And to get that, the waves have to be perfectly out of phase. They have to be mirror images, separated by exactly 180 degrees.
So if the noise wave is at its peak, let's call it a +1 of pressure.
Our headphone needs to generate a wave that's at its absolute bottom, its trough, a -1.
And +1 + -1 equals
0. Silence. The waves cancel each other out right at your eardrum.
So active noise cancellation isn't a passive shield. It's not like wearing earmuffs. It's an active system that is constantly creating sound.
It's creating a very specific anti-sound, a perfect mirror image of the unwanted noise.
And this is where the engineering gets really, really tricky, I'd imagine.
Oh, absolutely. Because the energy doesn't just disappear. What happens is a local cancellation. It has to be perfect. The energy of the noise and the energy of the anti-noise are in this perfect balance.
Right at your ear.
Right at your ear. But what if the timing is just a little bit off? Even by a few microseconds.
Ah, so you're saying the anti-noise wave arrives late to the party.
A tiny bit late. Instead of being 180 degrees out of phase, maybe it's 170. It doesn't cancel the noise anymore. It can actually make parts of it louder.
So that's why some sounds get through. It explains why ANC is incredible for, say, the low drone of an airplane engine.
Yes, those waves are long and predictable. The processor has plenty of time to see the wave coming, calculate its opposite, and generate it.
But it's not so good with sudden, high-pitched sounds, like, someone talking next to you or a baby crying.
Exactly. Those waves are short, they're chaotic. By the time the headphone's microphone hears the sound and the chip creates the anti-sound, the original sound has already gone past your ear. It's too fast to catch.
So the silence you get from ANC isn't really an absence of anything, so not empty space.
Not at all. It's actually the result of an incredibly intense high-speed battle happening right at the entrance to your ear.
So what this means for you, when you flip that switch on your headphones and the world just falls away.
Remember that the quiet you're experiencing isn't emptiness. It's actually a violent tug of war.
A perfectly balanced fight between two opposing forces.
A kind of acoustic stalemate. And maybe that's the thought to leave you with, that true engineered quiet is achieved not through peace, but through a perfect molecular level conflict.
Welcome back to the Deep Dive. Today we're getting into something I think we all find a little bit magical. Active noise cancellation.
Or ANC.
Exactly, ANC. We've all had that moment, right? You're on a plane, you flip a switch, and the world just goes quiet. But how does that actually work? What's the architecture behind the silence?
Well, that's the key word, isn't it? Architecture.
Okay, so let's unpack that. The basic idea is creating an anti-wave, a mirror image of the sound, to cancel it out. But the real challenge, the engineering problem, is all about placement.
It is. Where you put the microphone, the processor, and the speaker, that's what determines if it works or if you just get, a horrible squealing sound.
And that's because, at its core, ANC is really a prediction engine.
It's totally a prediction engine. It has to guess what noise is coming and deliver that anti-noise wave at the absolute perfect moment. The whole architecture is about how it makes that prediction.
So let's start with the first approach then. The one I've seen called the Sentry. That's feed-forward ANC.
Right. And Sentry is the perfect word for it because in the system, the microphone is on the outside of the ear cup.
Okay, so it's standing guard.
Exactly. It hears that plane engine, that background hum, before it even gets to your ear.
And that gives the processor, the DSP, a bit of a head start to work.
A hugely valuable head start. And because it has that time, it's really, really good at canceling those constant mid to high frequency sounds, the steady drones.
That makes sense. But if it's listening on the outside, how does it ever know if it actually worked? I mean, inside, by my ear.
It sells
That sounds like it's just firing off an anti-wave and hoping for the best.
That's it. You've hit on the critical flaw. It's an open loop.
It never checks its work.
Never. So if your headphones don't fit quite right or, a gust of wind hits that microphone, it might actually be creating more noise.
Yeah.
And it has no idea. It can't correct itself.
So that brings us to the second system, the corrector. This must be feedback ANC.
Yes, the polar opposite in design. Here, they put the microphone inside the ear cup.
Okay, so right next to the speaker in my ear canal.
Right there. So instead of predicting, it's listening to what you are actually hearing. The final product, noise and all. If it hears any sound that shouldn't be there, it corrects it on the spot.
Which means it's a closed loop. It's constantly checking its own work, adjusting for fit, for movement.
It's tailored perfectly to your ear in that exact moment. It is self-correcting.
But the flaw there seems obvious. It has to hear the noise first to cancel it. That introduces a delay, even a tiny one.
It does. It's reactive, not predictive.
And if that timing is even slightly off, that's when you risk that awful high-pitched squeal, the feedback loop everyone dreads.
Precisely. That latency is the trade-off, which of course is why the industry didn't just stop there.
Right, which brings us to hybrid ANC, the gold standard.
The gold standard. It's simply using both systems at once.
So you have the feed-forward mic on the outside, doing the heavy lifting.
Yes, handling the big, predictable noises. And then you have the feedback mic on the inside, which is just there to sort of polish the result. It cleans up any sound that leaks through.
And this is what's in the top-end stuff, like the AirPods Pro or the Sony XM series headphones.
Exactly. It's the best of both worlds, prediction and correction working together.
Okay, so if this hybrid system is so good, why are there still sound it just can't touch? I can still hear myself chewing. A dentist's drill is still... Well, a dentist's drill. What's the barrier?
That's where we hit a fundamental physical limit.
Good.
It's called bone conduction. ANC, no matter how good it is, can only cancel sound traveling through the air. Air-conducted sound.
So it can't stop a vibration.
It can't. That chewing sound, that drill, it isn't just traveling to your ear through the air. It's vibrating through your jawbone, through your skull, directly to your inner ear, your cochlea. And no anti-wave in your ear canal can stop a vibration that's already inside your head.
That's a fascinating distinction. So to sum it all up, you have feed-forward, predicting the future, feedback, critiquing the past.
And together, in a hybrid system, they manage the present sound.
So I guess that leaves one final thought for you, our listener. If ANC can only filter the world around you, but not the sounds your own body creates, what does that say about our personal experience of silence?
It says you can filter the world, but you can never, ever entirely filter yourself. There's a physical boundary to the silence technology can give you. Welcome to the deep dive. So today, we're digging into something most of us use every day. Active noise cancellation. ANC. We all know that magic moment. You're on a plane, you flick a switch, and that engine drone just, vanishes. We want to unpack what's actually happening under the hood.
And right away, the biggest challenge isn't what most people think. It's not the physics of sound waves, not really. The single greatest hurdle is time. Pure, brutal speed. Sound moves at about 343 meters per second. Think of it like this. That's roughly 1 foot per millisecond.
1 foot per millisecond. Okay, so inside a headphone cup, the distance from the outside to your eardrum is, what, an inch?
Exactly. Which means if a noise happens right there, the entire system has maybe 0.07 milliseconds to do everything it needs to do.
0.07. That feels impossible. What does it even have to do in that time?
Well, it's a 5-step process. First, digitize the incoming sound. That's the ADC, the analog to digital converter. Then analyze that digital signal. What's the frequency, the amplitude? Then you have to digitally generate the opposite wave, the anti-wave.
The mirror image of the sound.
Precisely. Then convert that anti-wave back into an analog signal with a DA, and finally physically move the little speaker diaphragm to push that sound out.
All of that in 0.07 milliseconds.
Before the original sound wave even finishes crossing that 1-inch gap.
So let's talk about what happens when it fails, when it misses that deadline. You get what's called a phase mismatch, right?
Yeah, and that's where things get really interesting. The anti-wave arrives late, so it's not perfectly 180 degrees out of phase anymore.
And a little bit late just means it doesn't cancel as well.
A little bit late is just inefficient, yeah? But what if it's so late that it arrives at 0 degrees out of phase? So it's perfectly in phase with the noise. It adds to it.
It doesn't just add to it, it doubles it. It doubles the perceived sound pressure. And that's the uncomfortable whooshing pressure you feel in cheap ANC headphones. So that feeling is literally the sound of the computer losing the race against time.
That's exactly what it is.
Okay, but environments change. A train's rumble isn't perfectly constant. How does the system adapt to keep up?
It uses something called the LMS algorithm.
Ah.
Least means squares. You can think of the process of the DSP as a frantic DJ trying to match a beat.
A blindfolded DJ.
Blindfolded DJ, yes. It makes a guess at the anti-wave, and then a tiny microphone inside the ear cup, the error mic, listens to the result.
And it tells the DJ how they did.
It tells the DJ, nope, you're off, or a little sharp, and it feeds that error back. The LMS algorithm then uses that feedback to adjust its settings, its filter weights, up to 48,000 times every second.
Wait, 48,000 times a second. If it's adjusting that fast, why can't it cancel out, say, a sudden shout? Or the classic example, a baby crying on a plane?
And that is the absolute core of the problem. It's about predictability versus chaos. An airplane engine is periodic. The sound wave repeats itself over and over in a very predictable way. The algorithm can easily forecast what the next millisecond of sound is going to look like.
It sees the pattern.
It sees the pattern. But human speech, a shout, a cry, that's non-periodic. Yeah. It's transient. It's acoustically chaotic.
There's no repeating pattern to lock onto.
None. By the time the system has analyzed one syllable, like bah, and built the perfect anti-wave for it, the person has already moved on to the next sound, da. The target is always moving faster than the prediction loop can keep up.
So the whole strategy is reactive, and for some sounds, that's just not good enough. So where does this go in the future? Is it just about faster and faster chips?
Not entirely. The shift we're seeing is from reactive to proactive ANC.
Proactive? How can you cancel a sound before it happens?
Well, you use other sensors. Imagine bone conduction microphones that detect your own voice vibrations before the sound even leaves your mouth. Or even tiny cameras that use lip-reading AI.
So you could prepare the anti-wave before the sound even hits the main microphone.
Exactly. You give the system a head start in the race.
It's just amazing. The silence we're all buying is really just computation being performed at the very, very edge of physics.
That's the perfect way to put it. It's a computer trying to outrun sound over a distance of just a few centimeters.
An incredible deep dive. Thank you.
And it leaves you with a final thought. You know, if the difference between golden silence and doubled noise in our headphones is measured in microseconds, and it's decided by the speed of a tiny chip, what other experiences are being dictated by this same race? Think about a self-driving car's reaction time. Is its technology finishing its calculations faster than physics is unfolding on the road ahead?
Okay, let's unpack this. Welcome to the deep dive. Today, we are going from sand to silicon.
Yeah.
And it's this really surprising foundation of, well, all of modern computing.
The source material kicks off with this fantastic thought experiment.
The alchemist one.
The alchemist one, yeah. If you could show a smartphone to a medieval alchemist, they would just think it's pure magic.
Of course. No other explanation.
But the reality is actually stranger. We have literally trapped logic inside a rock.
And not some special, mythical rock.
No. Specifically silicon dioxide, which is, it's just beach sand.
So the whole mission for us today is to figure out how we take that sand, which is an insulator, and turn it into the most complex switch ever made.
Right. And to do that, you need the most fundamental unit. The atom of the digital age, if you will.
The MOSFET transistor.
Exactly.
And I think the best analogy, which the source uses, is a simple water faucet.
It's a perfect way to picture it,
You have your source, that's the water coming in.
which is the electrons in this case.
Yeah. The electrons, right. Then the drain, where they flow out.
Uh-huh.
And then you have the gate, the handle.
It's the handle. But here's the magic. With a real faucet, you turn the handle with your hand.
Sure.
In a transistor, that handle, the gate, is turned by another, much smaller electrical signal.
Ah, so a tiny current is controlling a much larger one.
That's the trick. That's how you get amplification and, logic.
But you can't build this out of pure silicon.
No, absolutely not. Pure silicon is, it's almost too perfect. It's this stable crystal lattice. It's boring, electrically useless.
So the solution, which feels so backwards, is to intentionally make it impure, to poison it.
We call that process doping. And we're not just throwing stuff in there. We're injecting very specific impurities to change its personality.
And we need two types of that personality.
Right. First, you have what's called N-type.
Okay.
We add phosphorus to the silicon. Phosphorus is an extra electron. It's just dying to give away. It makes material negative.
And then you need its opposite.
Partner, yeah, the P-type. For that, we add boron, which is missing an electron. It has what we call an electron hole that desperately wants to be filled.
So you have one material that wants to give an electron and one that wants to take one.
And when you smash them together, it was called a PN junction. And what that junction does is it basically acts like a one-way valve for electricity.
It forces the current to follow a very specific rule.
Exactly. And that's the channel that the gate can now control.
Okay, so now we have billions of these tiny microscopic rule-following switches. But how? How do you get from a simple on-off switch to rendering a 3D video game?
Well, that's the next leap, isn't it? It's all about how you combine them to build logic gates.
Like an AND gate.
An AND gate is a great example. You just wired two transistors in a row in series.
So the electricity has to get through both of them to pass.
Right. So the output is only on if transistor A and transistor B are on.
And if you put them side by side in parallel.
Then you get no OR gate. The current flows if A or B is on.
And that's it. That's how you start doing math.
That is how you start doing math. You combine those simple gates, AND E, or a few others, and suddenly you can build a circuit that adds.
Wait, really? The most complex thing a CPU does is just adding 1 + 1 over and over again.
That's the beautiful, elegant truth of it. You build a circuit called the adder, and once you can add, you can multiply. And if you can multiply, you can do literally anything a computer does.
So when you step all the way back, what does this actually mean?
I think the biggest takeaway from the material is that there's no brain inside your CPU. There's no magic.
It's just a city.
A city of billions of microscopic switches, all just flipping each other on and off in this massive cascading chain of dominoes.
Wow.
And that leaves you with a final pretty provocative thought.
Okay.
The thought a computer has, the final output you see on the screen. It's just the pattern the electricity makes as it flows through this maze we carved into stone.
So all this complexity, all this apparent intelligence, it's just the result of simple patterns happening at an unbelievable speed.
Happening inside a refined grain of sand. And when you really get that, it completely changes how you look at the device sitting in your pocket.
We all tend to operate under this powerful assumption, don't we?
Which one is that?
That if you just give a computer enough time, enough power, it can solve anything. And that, for every true statement in math, there has to be a proof for it somewhere.
Right. It's a very comforting thought. But it turns out it's just not true.
And that's what we're digging into today.
Exactly. Back in the 1930s, two thinkers, Alan Turing and Kurt Gödel, they kind of blew that idea wide open. They found what one of our sources calls a hard wall in the universe of logic.
A hard wall. I like that. So our mission for this deep dive is to explore these limits of logic. It's this genuinely unsettling idea that our whole digital world is built on a foundation that can be brittle.
Fundamentally brittle, yes.
So let's start with Turing, the halting problem. It sounds complicated, but the idea itself is actually pretty simple to lay out, right?
It is. The question is this. Could you write a perfect program? Let's call it the Oracle.
Okay, the Oracle. And its job is?
Its job is to look at any other program you give it and predict with 100% certainty if that program will eventually finish its job, halt, or if it's going to get stuck and run forever in an infinite loop.
And the answer is, you can't.
You absolutely cannot. The mathematical answer is a categorical no. It's structurally impossible.
So how do you prove something is impossible? You have to what, force it to contradict itself?
That's the genius of it. You feed the oracle a program that's designed to be a paradox.
A poison pill.
Basically, yeah. The paradox program says this. Hey, oracle, if you predict that I'm going to halt.
Then I'll do the opposite and loop forever.
Exactly. And if you predict I'm going to loop forever.
Then I'll just stop. I'll halt.
So no matter what the oracle predicts, the program is built to immediately invalidate the prediction. The oracle can't be right. Therefore, the oracle can't exist.
And that means there are problems that are just unsolvable by any computer ever.
We call them undecidable problems. A computer literally cannot calculate the future of its own behavior with total certainty.
Wow. So Turing showed a limit to computing. But Gödel, he went even further, didn't he? He went after mathematics itself.
He did. Gödel proved that in any logical system that's complex enough, like, say, basic arithmetic, there will always be statements that are absolutely true, but are fundamentally unprovable within that system's own rules.
Okay, that just feels wrong. How can something be true if you can't prove it?
Think of the classic liar paradox, the sentence, this sentence is false.
Right. If it's true, it's false. If it's false and it must be true, it just breaks.
That's it, exactly. Gödel found a way to write that paradox using the language of mathematics. He created a mathematical statement that essentially says about itself, I cannot be proven.
And since that statement is, in fact, true, but the system can't prove it.
That it means truth is a much bigger concept than proof. There are truths that logic can never reach.
So let's bring this home. What does all this mean for us, for our technology? I mean, this isn't just a thought experiment.
Not at all. It defines the hard limits of things like artificial intelligence and cybersecurity.
Yeah.
We run straight into the halting problem all the time.
How so?
Well, think about a virus scanner. You want it to find all viruses, right?
Of course.
But we can never, ever write a virus scanner that is guaranteed to catch all possible viruses.
Yeah.
It's impossible.
Wait, why?
Because figuring out if a piece of code is malicious is, deep down, a version of the halting problem. You're trying to predict its future, potentially harmful behavior. And we already know that's undecidable.
So the perfect anti-malware system can't exist. That is not comforting.
It isn't. It means we can never build a machine that knows everything. It means when your computer crashes or a system gets stuck in a loop, it might not just be a bug. It could be hitting one of these fundamental blind spots in logic itself.
So the big takeaway here really is that logic is brittle. Our entire digital world, all these castles we've built, they're sitting on a foundation of paradox. At the extremes, things just become unpredictable.
And that leaves you with a really big thought, doesn't it? If mathematical truth can exist beyond what we can prove, what else is out there? What other parts of our world, maybe in politics or even physics, have these boundaries where knowing something is completely separate from being able to prove it?
Okay, let's dive in. We're here to unpack this really monumental shift in computing.
Right.
We're moving away from that old rigid logic, the whole if X then Y way of programming that we all learned.
A system that just completely falls apart with real-world complexity.
Exactly.
I mean, think about it. How do you write rules to identify a cat? A black cat, a white cat, one that's, curled up in a ball or half hidden by a plant.
You can't. It's impossible.
You'd never finish writing the rules. So the machine has to build its own kind of, its own intuition.
Mm-hmm.
And our mission for you today is to really get into the mechanics of how it does that.
Starting with the absolute core building block, the digital neuron.
The perceptron.
Right, the perceptron. So it takes in an input like, say, all the pixels from that cat picture. But the real magic is in the weights and the biases, isn't it?
That's where the learning is stored. The weight is like a volume knob.
Yeah.
It tells the network how much this specific pixel should matter.
And the
bias is just the threshold. It's the must be this important to fire line. But here's the key. They all start out completely random. The network is just a blank slate.
So it's going to make a wild guess at first.
A terrible guess.
So we showed a cat, and it says dog. That's the forward pass. But how does it then correct millions of those little volume knobs all at once? I mean, if the change is tiny, won't that take forever? How does it even know which way to turn the knob?
That is the elegance of backpropagation. So step 2 is the loss function. It's just math that calculates the size of the mistake, the exact distance between its guess, dog, and the truth cat.
Okay, so it knows how wrong it is.
Precisely. And for step 3, the backward pass, it uses calculus, specifically gradients, to work backward from that error The gradient finds the slope, the mathematically fastest way to reduce the error.
So every single adjustment, every tiny turn of the knob is the most efficient possible step toward getting it right.
A most efficient step. And then you just iterate. You do that a million times, a billion times until the entire network is tuned.
And once it's tuned, this is where things get, for me, just completely mind-bending, because we can't actually picture how an AI thinks.
Not even close.
Yeah.
We see the world in, 3 dimensions? Maybe 4 if you're generous.
A big neural network is operating in thousands. I saw one stat, a large language model can have 175 billion parameters. That's 175 billion different axes of thought. It's just not a human-scale concept.
And if you connect that to the big picture, a concept, whether it's something simple like cat or wildly abstract like justice, it's just a location.
A location.
A coordinate vector in that massive hyperdimensional space. So when a model like ChatGPT is talking to you, it's really just navigating this enormous abstract map where similar ideas are physically clustered together.
Which brings us to the really unsettling part, the black box problem. We know the math, right? We know it's just matrix multiplication on a massive scale, but we have no idea what it has actually learned.
None. We never told it to look for whiskers or pointy ears and just figure that out on its own by analyzing the data.
We're not the architects of the logic anymore.
No, we're the gardeners. We just provide the water, the data, and the sun. But the way the plant actually grows, its internal structure, is a mystery to us.
So, wrapping this up for you, the listener, what's the core thing to remember?
That modern AI is not logical in the way a human is. It's statistical. It's a master of correlation and probability, not deduction. It runs on patterns, not rules.
And the final thought to leave everyone with.
I think the most powerful description I've ever heard is this. We have built a probabilistic hallucination engine.
A hallucination engine.
That we have then meticulously tuned to hallucinate the truth. So the question to mull over is, what happens when that kind of statistical intuition starts to replace our traditional deductive human logic?
Welcome to the Deep Dive. Today, we're getting right to the heart of all digital security.
We really are.
Our whole mission here is to understand the mathematical trick that lets you send a secure message online without ever meeting up to share a secret key.
And crucially, the one future threat that's pretty much guaranteed to shatter that entire system.
It's kind of a strange concept, isn't it? For centuries, security meant hiding the key.
Exactly. But in the 1970s, this idea of public key cryptography, specifically the RSA algorithm, it just flipped everything on its head. It uses pure math to let the entire world know what your lock is.
But only you have the key that can open it.
Right. It's all about exploiting a fundamental asymmetry in mathematics.
Okay, so let's dig into that. The famous trapdoor function. Why is this gap in difficulty? Why is that the foundation for basically everything we do online?
Well, because it's about what computers find easy versus what they find almost impossible. It's incredibly easy for any computer to take two huge prime numbers, say two numbers that are each 100 digits long, and just multiply them together. It can do that in a fraction of a second.
That's the trapdoor opening.
That's the easy way in. But trying to go backwards, taking that massive 200-digit product and trying to find the two original prime numbers that made it.
That's the hard part.
It's computationally near impossible. For today's computers, we're talking billions of years of just guessing and checking. Brute force.
Wow. So that's the core shield. And this asymmetry gives us the two keys in the RSA system, the public key, which anyone can use to like a message for you.
Precisely. And the math behind it starts with those two giant secret prime numbers. I can call them P and Q. You multiply them together, and you get an even bigger number, N.
The modulus.
The modulus, exactly. And that number N is a core part of your public key. It's the lock that you hand out to everybody, kind of sets the playing field for the encryption.
So everyone in the world can know N, this massive number, but they have no way of figuring out the original P and Q that made it.
Right. And without P and Q, you can't create the private key.
So how do P and Q let you work the magic in reverse?
Because knowing them is the secret ingredient for the mathematical trick that builds the private key. It's a calculation, a kind of reversal called a modular inverse. If you don't know P and Q, you simply can't do that calculation. Our entire digital world is basically hoping that factoring N is just too big a job for every computer on the planet combined.
But see, that's what feels so fragile. We're just relying on a calculation being too long to solve. And that assumption is, well, it's about to break.
It is. We already know the tool that will break it. It's not theoretical.
Shor's algorithm.
Shor's algorithm running on a stable, large-scale quantum computer. Now, a classical computer tries to check factors one by one, but a quantum computer, it works with probabilities. It can essentially check all the possibilities at once.
So a problem that takes a normal computer billions of years.
A quantum computer could solve it in minutes, maybe less. It would just spit out P and Q almost instantly.
And if that happens, the private key is exposed, which means all public key encryption, the thing that protects every bank, every government, every password,
Just stops working.
Yeah.
The shield shatters.
And that's the global panic right now, this race to invent post-quantum cryptography.
It's a huge, highly funded race. And really, the key takeaway for you listening at home is that your digital safety hangs by this single fragile thread. It's an assumption that the hardware to break the code is just too hard to build right now, not that it's mathematically impossible.
It really changes how you see that padlock analogy, doesn't it? When you realize the combination can be instantly found by a machine that just plays by different rules.
Absolutely. And that leads to the real deep dive question, if this bedrock idea, the simple difficulty of factoring, can be broken by a new kind of technology, what other fundamental assumptions of our digital world are just as fragile? What else is just waiting for its own quantum level disruption? All right, so for today's deep dive, we're jumping into elliptic curve cryptography, ECC. Our mission here is to really get the geometry that's securing, well, pretty much the entire modern web.
Yeah, it's the math that makes your digital life both fast and secure.
So let's start with why we even need it. The old champion, RSA, is getting, I guess the word is heavy.
Heavy is a good word. It's slow. To be secure, RSA needs these massive, massive keys.
We're talking 4096 bits.
Exactly. And that size directly translates to slower connections, more bandwidth, and it just drains your phone's battery every time you connect to something securely.
And this is where ECC comes in as the solution.
It is. And what's so fascinating is just the sheer efficiency. You get the exact same level of security as that giant RSA key, but ECC does it with a tiny 256-bit key.
That's a huge difference.
It's security miniaturized, and that's why it's the standard now. I mean, for everything from Bitcoin to iMessage to just your regular web traffic.
Okay, so let's unpack that. We're actually leaving the world of number theory, where RSA lives with all its prime numbers, and we're stepping into something called algebraic geometry.
That's right. We are hiding secrets in the actual shape of a curve. The equation is y squared equals x cubed plus x plus b.
And when you draw it, it doesn't look like an oval or a circle. It's more like a sideways bell shape.
It is, but here's the really critical part for the cryptography. We don't use the smooth, continuous curve you draw on paper. We define it over a huge but finite grid of numbers. It's called operating over a finite field.
Ah, okay. So instead of a predictable smooth line, we're talking about a scatter plot, a bunch of discrete points bouncing around inside a massive box.
Precisely. And that discontinuity is what makes the path so hard to reverse. And this setup gives us this one sort of magical property.
Which is?
If you draw a straight line through any 2 points on that curve, that line is guaranteed to hit the curve in exactly one other spot.
And that's the core operation, the addition on the curve. So you take this geometric rule and you turn it into a kind of game, like mathematical billiards.
That's a perfect analogy. We're creating a path that's really easy to follow forward, but it's completely impossible to trace backward.
How does that work?
So you start at a point, let's call it point A. You draw a line from it, find where it hits the curve again, and then you reflect that new spot over the x-axis to find point B.
And you just do that over and over again.
You repeat that operation, say, n times. This is called scalar multiplication. And if you know n, finding the final landing spot, we'll call it z, is trivial.
Okay, but wait. If the forward path is just repeated addition, why isn't reversing it just simple division? Where's the trap door?
That's the genius of it.
Yeah.
Because we're on that finite field, that scatter plot of points, the path looks completely random. So if I give you the start point A and the end point Z, and I ask you, how many times did I bounce the ball? Trying to find that number n is computationally impossible.
I see. That's the elliptic curve discrete logarithm problem.
That's it.
So we're hiding our secrets, our private keys, not in a big number, but in the number of hops, in that untraceable distance and along this bouncing path.
It's security built on elegant geometry instead of just brute force numbers.
So what this really means for you, the listener, is that ECC is why your banking app is fast and why your encrypted messages don't destroy your data plan.
It is. But this reliance on something being impossible does raise a very important question for the future. The security of, well, the entire digital world rests on the fact that you can't work backward on this path right now.
But what if you could?
What happens if new mathematics, or maybe more realistically, a powerful quantum computer, suddenly solves the discrete logarithm problem? What happens to global finance and communication when the geometric foundation of all their security just vanishes overnight?
So here's a thought for you. How do you prove, a secret, say a password, without ever actually typing it in and, revealing it?
That's the question, isn't it? Especially now. It feels like every big company gets breached,
Yeah.
and handing over your credentials, it just feels like an unnecessary risk.
A huge risk. And that's where this whole idea comes in, this thing called zero-knowledge proofs, or ZKPs.
Exactly. It's a way to get trust without truth. That's the core concept.
Trust without truth. That sounds like a complete contradiction. So how do we even begin to unpack that?
Huh.
I think we have to start with the classic analogy.
We have to. Alibaba's cave. It's really the best way to get it without getting lost in the weeds of cryptography.
Okay, so paint the picture for us.
All right. Imagine a cave that's shaped like a ring, a complete circle. But halfway through, there's a magic door that blocks the path.
A magic door that needs a secret password.
Right. And we have two people. We've got Peggy, who is our prover. She says she knows the magic word.
And then you have Victor, the verifier. He's skeptical. He wants proof.
He wants proof.
Right.
But, and this is the key, he can't learn the secret word itself. Peggy's knowledge has to stay private.
So Peggy goes into the cave alone. She can take the left path or the right path. Victor doesn't know which one.
He has no idea. Then he walks up to the entrance and shouts, "Come out the left path."
Okay. So if she happened to go down the left path, that's easy. She just walks out.
Trivial.
Yeah.
But if she went down the right path, she's now stuck at the magic door.
And she has to use the secret word to open it so she can come out the left side as he demanded.
Exactly. From Victor's perspective, she successfully met his challenge. But hold on a second.
Yeah, I was going to say that could have just been luck, right? A 50-50 chance she picked the correct path to begin with.
That's the critical part. One time proves nothing. It's all about repetition.
So they do it again and again.
They do it, say, 20 times. The odds of her just getting lucky and guessing the right path 20 times in a row, it's astronomical.
It's less than 1 in a million.
Right. So after 20 successful runs, Victor is mathematically certain she knows the secret. And yet she never once had to tell him the word. He learns zero about the secret itself.
That's the zero knowledge part. It's complete, it's sound, and he learns nothing. So that's a great story, but how does this cave analogy translate to the real world? What are the actual applications?
Well, the implications are just huge. Think about identity verification.
Okay, like proving your age.
Exactly. You can prove you're over 21 without ever revealing your actual birth date, or your name, or your address. The system just gets a yes or no confirmation.
So the bar's website doesn't need to store my date of birth on some server waiting to be hacked.
Precisely. The data is never aggregated. The target is eliminated. What about finance?
How would that work? I mean, a seller needs to know I can actually pay for something.
Sure, but they don't need to know your exact bank balance. With a ZKP, you can prove the statement, "My account balance is greater than the purchase price," is true.
Without revealing the balance itself. The bank and the network just verified the proof.
The math checks out. That's all that matters. It even extends to things like civics, like voting.
So you could prove that you cast a legitimate ballot without anyone being able to know who you voted for.
Yes. It protects the integrity of the vote and the privacy of the voter at the same time.
This feels like a fundamental shift then. We're moving away from needing to trust people or entire institutions with our data.
That's the takeaway. You don't need to trust the person. You don't need to trust the company.
You just need to trust the math.
The math becomes the foundation of trust. If the algorithm is sound, the proof is absolute.
So if we can replace these institutions, banks, voting systems, identity platforms, with pure mathematics, it makes you wonder, what else could be rebuilt on this foundation?
It does, and that really leaves you with a final question to think about. If math provides this kind of absolute verifiable truth, what role is left for human accountability in a system that only trusts computation? Welcome back to The Deep Dive. Today we're going to be talking about the source code of life itself, DNA. For the longest time, science was, it was all about just reading it, sequencing the letters, the A, C, T, and G.
Exactly. But now the game has totally changed. Now we can actively write it.
We can edit the code.
And that's our mission for this deep dive. To unpack the mechanism of CRISPR-Cas9 and maybe more importantly, the huge ethical questions it raises, the whole paradigm has shifted. Life is no longer just a mystery. It's become a read-write medium.
And what's so wild about this is that the tool itself, it wasn't invented in some high-tech lab.
Not at all.
It was discovered, right, in bacteria. It's an ancient immune system.
That's it. It's this incredibly elegant defense mechanism. So a virus attacks a bacterium, and the bacterium fights back. It literally cuts off a little piece of the virus's DNA, and it stores it.
It stores it. So it's building a kind of database of all its enemies.
That's a perfect analogy. It's a biological mugshot library, and it's stored in a place called the CRISPR array.
Okay, so it has the mugshot. What happens when that same virus tries to attack again?
Well, that's when the cell brings out the enforcer, this protein called Cas9.
The executioner.
The executioner, exactly. Cas9 takes the invading DNA and compares it to all the mugshots in the library.
And if it finds a match, it doesn't just, like, flag it.
Oh, no, it's much more direct. If there's a match, Cas9 acts like a pair of molecular scissors. It just snip.
It cuts the viral DNA.
And that neutralizes the threat. It's simple, powerful, and it's been happening for billions of years.
So that's the ancient system. The human revolution, the big breakthrough, came from Jennifer Doudna and Emmanuel Charpentier.
Right. They had this incredible realization.
They figured out we could hijack it.
We could reprogram it. I mean, if the bacterium can tell Cas9 what sequence to cut, then we can tell it what to cut.
How do you do that? How do you give it new instructions?
You create something called a guide RNA. It's basically a synthetic instruction that you design. It leads Cas9 to find a very specific sequence that we choose.
Any sequence. So you could, in theory, point it right at the gene that causes, say, Huntington's disease.
Absolutely. You tell Cas9, find this and cut right here.
And after it makes the cut,
the cell's own natural repair system kicks in. It rushes to fix the break, and that moment, that's our window.
To slide in a new piece of code?
Exactly. We can slip in a new, corrected piece of DNA. So what we've effectively built is, well, it's CTRL plus F, find, and CTRL plus V, paste.
For the source code of life.
It's staggering to think about.
It really is. And that brings us right to the ethical stakes, because there are two very, very different ways we can use this power.
And we have to be so clear about the distinction between them.
Okay, so what's the first kind of editing?
First, you have somatic editing. Think of this as medicine. You're editing the DNA of a living person's body cells to fix a condition.
Like curing sickle cell in a patient.
Precisely. And the key thing is, those changes die with that patient. They are not passed on to their children.
Right. But the second type, that's where the gravity of this really sinks in.
That's germline editing. This is where you're changing sperm, eggs, or embryos.
So the changes become heritable.
They become permanent. They get passed down to all future generations. At that point, we're not just curing a disease in one person.
We are literally directing our own evolution.
We're seizing control.
So if we just boil all this down, is the conclusion that the line between what is born and what is made is just dissolving?
That's the crux of it. The knowledge we have has fundamentally changed our relationship with our own existence.
Life is a read-write medium.
It is. And we want to leave you with this final thought to consider. The pen is now firmly in our hands. So when we can direct our own evolution, what does responsibility even look like for all the generations that follow?
That's the question we leave with you.
Welcome to the Deep Dive. So today we're going deep on, well, mapping what some people call the wires of the soul, the connectome. And our mission really is to unpack this foundational idea that you, and I mean everything, your memories, your personality, your fears, is all physically encoded.
Right, in the unique pattern of connections, the synapses between your brain's neurons.
Exactly. So if your mind is information, the connectome is the map of that information.
The precise map. And what's so fascinating here is that this isn't just, science fiction theory. We actually have a proof of concept.
On a tiny scale, though. Right?
The very tiny scale. We have successfully mapped the complete connectome of exactly one creature, the C. elegans worm.
And that's the one with only, 302 neurons?
Just 302. So we know every single connection, every single synaptic path.
Which allowed for, well, a pretty incredible test.
A profound one, yeah. They took that map, simulated it in a computer, and essentially put that virtual mind into a virtual body.
And it moved.
It swam and reacted to virtual walls. It behaved just like the biological worm would.
So, was it alive? I mean, did we upload a worm?
That is the ultimate question. And it's the perfect bridge, because if we go from 302 neurons to the human brain...
The scale just explodes.
Right.
So what does this look like for us?
The jump is It's staggering. A human brain has approximately 100 trillion synapses.
100 trillion.
And if you wanted to store that specific map, your connectome, as digital data, you would need about 1 zettabyte.
Okay, put a zettabyte in context for me.
In 2016, that was equal to all the digital content of the entire world.
The entire world's data for one brain. So this is really an information storage problem before it's anything else.
It's a huge part of it.
But wait, a quick question on that. Isn't the brain constantly changing? You know, the connections aren't static. So how useful is a static map?
That's the nuance. Exactly. You can't just map the connection. You have to capture its weight, its plasticity. It's much harder.
Yeah.
But, okay, let's just set the technical challenges aside for a moment. If we assume the connectome theory is true, the implications for mortality are huge.
How so?
Death isn't total destruction anymore. It's the scrambling of that essential information.
The data is corrupted, not deleted.
Precisely. And if that map could be preserved, stored, read, then the mind could, in theory, be restored.
Which brings us to the core philosophical concept behind all of this, right? Substrate independence.
Exactly. Substrate independence is the argument that a mind is essentially a function. It's a pattern, an algorithm.
An algorithm.
And that algorithm doesn't care what hardware it's running on. It could be our biological wet meat brains, or it could be advanced silicon chips. The physical medium is irrelevant.
So the information is what matters, not the vessel.
That's the idea.
So to pull all this together for you, we are approaching a moment where if we can solve that zettabyte storage problem and the scanning problem, we might be able to back up a human consciousness.
Your personality, your memories.
The whole you, like backing up a hard drive.
But this raises a really important question that goes beyond the technology. You know, the map is not the territory.
Right.
So if we successfully copy and run your unique human connectome on a machine, we haven't destroyed the original. There would be a copy of you running on a different substrate.
So there would be 2 of you.
Exactly. Which one is the original you?
Something to ponder.
You know, we've spent centuries explaining the machinery of the physical world.
Oh, absolutely.
Things like sound waves, DNA, transistors. I mean, science has been incredibly effective at breaking down, you know, the nuts and bolts of existence.
It really has.
But after all that, there's this one fundamental mystery left. Some people even call it the final frontier of knowledge.
And it's a big one.
Right. And the question at the core of it, the deep dive we're taking you on today, is basically this. Why does it feel like something to be you? We're unpacking that ultimate puzzle, the one known as the hard problem of consciousness.
What's so useful here is how the philosopher David Chalmers really structured this whole debate. He divided consciousness into 2 kinds of problems.
The easy and the hard.
Exactly. First, you have the easy problems.
Yeah.
And that name is, well, it's a bit misleading. They're essentially engineering puzzles that the brain solves.
So what does that include?
Things like how we focus our attention, or how we process sensory data like light, or even how we can report on our own mental states.
Okay, so why are those easy? They sound pretty complicated to me.
They're called easy not because they're simple, but because we can, in theory, map them to physical functions. We can literally see the neurons firing. We can see the machinery at work.
Right. But even if we solve all of those, if we know exactly how every neuron processes the color red, we still face that huge sticking point.
The hard problem.
The hard problem. Why is all that processing accompanied by an inner subjective experience? Why does red feel like anything at all?
That is the core of it. It's the difference between function and feeling. You know, thermostat processes data. It measures temperature and flips a switch.
But it doesn't feel cold.
It doesn't feel cold, and that's the mystery. Our brains process data, but why does that generate this inner world, this awareness?
Which leads us straight into this bizarre idea of the philosophical zombie.
The P-zombie.
Exactly. Why aren't we just these biological robots acting exactly like humans, laughing, crying, saying, ouch, but with no inner light, no feeling inside at all?
It's a huge challenge to a purely physicalist view of the world. And if we say we're not P-zombies, then we have to explain that inner feeling. And the theories trying to do that, well, they get pretty wild.
Okay, so what are the main contenders?
The first one is probably the most straightforward. It's materialism. It suggests that the solution to the hard problem is just hidden in the complexity.
So we just haven't figured it out yet.
That's the argument. That once we fully understand the brain's machinery, the feeling will just be explained away as a function. The ghost is just the hum of the machine.
But then you have the really radical alternative to that,
Oh, yeah. Panpsychism.
which says consciousness isn't an emergent property at all.
It's a mind-bending idea. Panpsychism argues that consciousness is a fundamental property of matter, just like mass or charge. It suggests every atom has a tiny spark of proto-consciousness.
So the universe is conscious all the way down.
In a way, yes. And our brains are just where these tiny sparks combine into something complex enough to be a human mind.
And what about the third one, the theory that tries to actually measure it?
Integrated Information Theory, or IIT. Now, this one is fascinating because it proposes a mathematical measure for consciousness, a number called PHY.
PHY.
Right. The theory says that consciousness is all about how integrated a system is. If a system is more than the sum of its parts, if its information is irreducible, it has a high PHY, and therefore it's conscious.
Okay, so this is where the philosophy suddenly becomes very, very practical.
With the rise of AI, absolutely.
The P-zombie problem is becoming a real engineering question. If we build an AI that cries and begs not to be turned off, is it just simulating fear, or is it actually feeling fear?
And that's the paralysis. Because science has no consciousness detector.
Right.
We can measure behavior, we can measure complexity, but we can't access that inner subjective feeling in anything but ourselves.
Wow.
So if you step back, the big takeaway is it's really profound. We've mapped the universe, we've peered through all the doors of perception, and we just found a mirror at the end of it all. The observer, you, the listener, is the greatest mystery.
So the universe has, in a way, woken up to look at itself, and we are those eyes. And the provocative thought we want to leave you with is this. What does it truly mean to live in a universe that has developed the capacity for self-awareness? Something to think about until our next deep dive.